Bismillah Rahman Rahim. Let me first review the CCR model. Let me have n decision-making units with input vector which is semi-positive and output vector that is also semi-positive. Note that, for example, when we say xj, that is the inputs of DMU j, and j can be from 1 to n, is semi-positive. It means that all its components x1, j2, xmj are non-negative, and at least one of these are strictly positive. We have the same for the outputs. We can gather the inputs and outputs in matrices, as you see. The CCR efficiency of DMU O, that O can be 1, 2, or n, is obtained by solving linear models, as you saw before. This is the CCR model in weighted form, and this is in envelopment form. Let me solve, for example, the left model LPO for DMU O, and let its optimal solution be U star and V star. And the optimal solution of DLPO also shows here. By using these models, we define DMUO is efficient, indeed CCR efficient, if first the optimal value of LPO is equal to 1, and second, there exists at least one optimal solution with all components positive. This is definition 2.1 that was in chapter 2. By using the dual in chapter 3, we had definition 3.2, which says DMUO is CCR efficient if 1. The optimal value of the DLPO is equal to 1, and second, the slacks are 0 for all optimal solutions of DLPO. This can be say also the slacks are 0 for the max slack optimal solution. We defined what is the max slack solution, indeed by solving DLPO first and obtaining the optimal theta star. We put theta star here in the constraints and maximize the summation of the slack variables in phase 2, and this solution is named max slack solution. Note that when the max slack optimal solution has a slack 0, this is true for all the optimal solution of DLPO. Another definition was Pareto-Koopman's efficiency, Mathematically, we can write that as here. There is no pair of x and y in production possibility set which dominates x o and a group. Means x is less than or equal to x o, y is greater than or equal to y o, and at least one of these relations for at least one component of x or y is strict, which means x and o is not equal to x o and x y o. This is another example. Another definition. All these definitions are equivalent, which means if we put P, the production possibility set for the CCR model, then DMUO is Pareto-Cook efficient if and only if it is CCR efficient with definition 3.2, if and only if it is CCR efficient in definition 2.1. Before proving, let's review a linear programming theorem named complementary slackness. Complementary slackness, we name it by CS. We have also a strong or a strict complementary slackness theorem. So we first introduce a linear programming model. Let A be an M by N matrix that when we put the index down, this means these are indeed columns of A, and when it is up, these are the rows of matrix A. So for example, A1, 1 is down, it is this column, and when put 1 up, A1 means this row of matrix A. Let B be M vector, X and N vector, C an N row vector, W M row vector, V N row vector, and S M vector. From linear programming, you know, if we have a linear programming as this can be shown also by this one. Its dual would be this model, which can be also write in this way. So we name P and D, and of course this is conversible, means if we the right be primal, the left is dual. As you know from the linear programming, we have the complementary slackness theorem, which says let X star and S star and W star and V star be any feasible solution to P and D, which means this one is for primal and this one is for the dual. These are feasible now. Then we have they are respectively optimal if and only if these conditions that names complementary slackness conditions are satisfied. You know, we can write the complementary slackness as this one or as it is in the parentheses. This means in optimality, for each pair of optimal solutions of primal and dual, the slack value of dual multiplied by its corresponding main variable in primal should be equal to 0, and we have the same for the slack value of primal and the main variable of dual. So this is named complementary slackness. Note that in complementary slack theorem, these conditions satisfies for all pairs of optimal solutions. And conversely, if two feasible solutions satisfies the complementary slackness conditions, they will be optimal for their corresponding models. And of course, we have another theorem named strong complementary slackness theorem, or a strict complementary slackness theorem, which we name it SCS theorem. You can see this theorem in the appendix of your DEA book. It was also in the linear programming book, Bazaro. Of course, in its problems, section 6. But note that this theorem says there exists at least one pair of primal and dual optimal points or solutions. Note that the difference. For complementary slackness, we have the complementary slackness conditions for all pairs, but here there exists at least one pair of optimal solutions with this is the strong or strict complementary slackness condition. Note the difference. We had the complementary slackness condition, but when multiplication of two numbers is 0, they can be also both 0. But for a strong complementary slack condition, at least one of these are positive. So the difference is these relations that say at least one of the pair that in complementary slackness condition their multiplication are 0 should be non-zero, that is positive. Now we use these theorems to prove theorem 3.1 for the CCR efficiency. This theorem says for the CCR efficiency, definition 3.2 and 2.1, this was in chapter 2 and this in chapter 3. This from LPO multiplier form of the model, and this for the envelope form of the model. Definition 2.1 says DMUO is CCR efficient if we have these two conditions. First, the optimal value of the model is 1, and second, there exists at least one optimal solution with positive component. Definition 3.2 says DMUO is efficient if and only if the optimal objective function value is 1, and the second condition is the S-likes are 0 for all the optimal solutions, or the S-likes are 0 for the max S-like optimal solution. To prove, we first assume that DMUO is efficient by definition 3.2 and show it is also efficient with definition 2.1. If DMU is efficient by definition 3.2, then its optimal value is 1. So from the duality that says the optimal values of the objective functions of primal and dual are equal, we also have, I should write E here. We also have the optimal objective function value of the dual should also be 1. This is the first condition for efficiency. And from the strict complementary slackness theorem, for at least one pair of optimal solutions, which means there exists an optimal solution for LPO and an optimal solution for DLPO, that we have the strict complementary slackness conditions as it writes for these models, similarly as you can see from here. Note that from definition 3.2, we have S-likes 0 for all the optimal solutions. So this means the component of U star and V star all must be positive. So DMUO is CCR efficient by DMU 2.1. Note that we obtained an optimal solution for LPO model with positive component. But conversely, let DMUO be CCR efficient by definition 2.1. This means there exists an optimal solution for LPO with the objective function of 1 and all the weights are strictly positive. Again, from the duality, we have, again, I missed E, or I don't know, maybe in the photo this is removed, I don't know why. Again, we have theta star is equal to 1 in DLPO because the objective function values of primal and dual are the same. So the first condition, we have the first condition. Now for showing that the S-likes for all optimal solutions, or the max slack optimal solution should be 0, let this be, this is not by, this is B. Any optimal solution containing this max slack optimal solution. From the complementary, so we consider an arbitrary optimal solution now, or the max slack optimal solutions, there's no difference. Now we should prove for the second condition that the slacks are 0. But from the complementary slackness theorem, we have, let's here have is correct. We have these conditions. That means the multiplication of the main variables optimal with the slacks variables, one from primal, another from dual, or conversely, should be 0. But since the component of U star and V star is not 0, this means that the slacks should be 0. So we have the slacks equal to 0. This could be for any arbitrary optimal solution, or containing max slack optimal solution. So the second condition for efficiency is also satisfied. So DMUO is CCR efficient by definition 3.2.